So I'll be presenting on execution markets. I'm from ChronoLogic, where we are finding solutions for scheduling transactions. So this is kind of something that came out of our research into scheduling transactions and then having a market to execute those transactions. And some patterns we've seen emerge from our project and from some other projects in the space. So to give like an intro to this, so what we're talking about when we talk about an execution market is the idea of delegated execution. What this means is either you are assigning a message which indicates your intent to execute a transaction that you sign, or you deploy a smart contract which holds the parameters that will be executed at a later date. So when you have this idea of a delegated execution, you also need the other side of that transaction. So you need someone to come in there and execute that for you. So it's kind of a one-layer abstraction on top of the gas market. So instead of paying for the gas to get your transaction included in a block, you're paying someone else to pay your gas. And this has a lot of interesting use cases. So the one we're all about at ChronoLogic is scheduled transactions. So we rebooted the Ethereum alarm clock project, and we're working on Chronos, which is a second generation scheduling protocol on Ethereum. So there's also transaction relayers. So some examples of these are if like a Dapp wants to have new users, but expects those users to be new to cryptocurrency in general, the Dapp can relay the transactions on behalf of users, and so can pay the gas costs for those new users who might not have cryptocurrency yet. There's also the idea that you can pay the gas costs in tokens instead of Ether. There's an EIP 1077, which kind of details the standard for these delegated executions, and there will be a talk on that later today by Alex Vandesanda. That could be a good one to attend if you're kind of interested in these delegated executions. And then a surprising example is the Mix-and-Miss zero knowledge mixer. So it involves sending an ether to a smart contract and then publishing a zero knowledge proof. The reason an execution market comes in for this is because to publish that zero knowledge proof on chain, you need to have some ether in an account, and sending ether to an account could potentially link that account to your identity. And if you're using a mixer, you kind of want to anonymize yourself. So using an execution market, you can publish the zero knowledge proof and have a third party execute that in a decentralized way. And then kind of the similar thing are the Watchtowers with state channels. These are a little different, but they were worth mentioning. So I'll go into some more examples with what we're working on at ChronoLogic, specifically with the schedulers. So on the left here, I have the way the Ethereum alarm clock works, which is by having this delegated transaction on-chain. And on the right, I show how it looks like when it's off-chain. So just to go through this, so when a user uses the Ethereum alarm clock, they send a transaction to the smart contracts. This transaction has all the data for the transaction that they want sent later, and then we have the executors, which we call time nodes, which are watching the Ethereum alarm clock contracts, and they keep track of each of these new scheduled transactions. And when those reach the execution window, they send the execution, and this transaction gets forwarded as it was set by the user. The off-chain way looks similar, except you don't actually send anything on-chain until you actually execute it. So you can get the same security guarantees by just signing a message with your private key that contains all the parameters of the transaction, and then publishing that to this network of executors, and then they will execute that on-chain through a contract which will verify that signature. So to get a little bit closer to the topic of the execution markets, so in the context of the Ethereum alarm clock, we have the time nodes, which are the ones which are watching the contract and executing. But we have a kind of a market where they all compete with each other to send this execution, because they will get rewarded a bounty payout when they execute. So we have, in this example, we have 5 time nodes. They all want the bounty, and they all send the transaction at the same time. Because this transaction can only be executed once, we come with this situation where there's a race condition, and only the first transaction, which is mined in the block, will actually be successful and give the time node the bounty payout, while the rest of the nodes who sent the transaction will end up reverting. And this might not seem like too big of a problem from a user perspective, because the user still gets the transaction sent that they scheduled. So from a user, they're happy because they got what they wanted. But from the perspective of the time nodes, all of the ones who weren't successful and got reverted will end up paying gas costs for that revert, while only one of them will get the bounty. So these are just numbers for illustration, but the idea is that if there's 5 nodes in this network and 1 out of every 5 times is successful, but the other 4 out of 5 will cost them money, you see a overall net loss in the network versus a net gain. So the incentive of providing the bounty actually starts to disappear if we have this race condition. So the kind of the major design we're looking at is to find a way for the time nodes, which are these layer 2 clients, which interact with the chain and watch the chain, the Ethereum main chain, but don't actually exist as smart contracts. They exist off the chain. We need to find a way for them to coordinate and not try to race each other to the execution. So I'll go into a few of the kind of design ideas that we're thinking about, and a couple of the mechanisms that we're thinking about. So the 3 major kind of topics that we have are the problem of incentivization, communication, and coordination. So the incentive is necessary to having an execution market that will execute the transaction, because without any kind of incentive, they have no reason to be running a client. It'll cost them money, and they won't do it pro bono. So incentive can be either tokens, or it might be more intangible things, such as a dApp that wants new users, might execute the transactions on new users' behalfs because it'll help out with their growth rate, for example. But the main idea is that there needs to be some kind of incentive in place. The next major problem we see is how do the nodes in this market communicate with each other? Or sorry, this one is how does the user communicate their transaction to the nodes? So with using the Ethereum alarm clock, this problem is solved by just emitting events on chain. So the nodes just watch the chain, and the user, when they schedule, the nodes will be alerted. But if we have an off-chain scheduling system where the user just signs a message, that doesn't hit the chain, so there's no way for the nodes to watch the chain in that instance. So we need some other kind of communication between the user and the nodes in this execution market. And this can be, for the most part, any kind of communication channel. It could be a peer-to-peer network. It could use, for example, like a libp2p communication channel. It could use Whisper potentially. But there needs to be some way for the user to publish the transaction and for the nodes to become aware of it. And another thing is a way that is preferably censorship resistance as well. And then the final issue is the coordination between the nodes. So this goes back to the race condition. So to prevent the race condition, we need some way for the nodes to decide which one will be the one that is sending the execution transaction. So there is a potentially on-chain kind of coordination solution, and this is kind of similar to like a proof of stake kind of thing, where the time node will stake some token or some ether, and then they specify what kind of transaction that they're willing to execute. So this will be a transaction at some time delta in the future, as well as some bounty payout. And then when a user schedules a transaction, the time node will get assigned to that transaction. And then their stake will kind of be attached to that transaction until they execute, and then they'll get the stake back. And if they fail to execute, another time node can come in and execute and get some of their stake instead. And so this is like an on-chain solution, and it works if we have the on-chain scheduling. But if we have the off-chain scheduling, which is the direction that we want to go in, because we can essentially move all of this off-chain and save all the gas costs, we can't use this kind of mechanism. And the off-chain coordination is a problem that is a little bit harder because so the properties of the time nodes in the execution market is a lot similar to like nodes in like a blockchain network. It's a permissionless network where we expect some kind of peer-to-peer communication and coordination. So it leads to essentially needing some kind of consensus between these time nodes. And this is something that we're still thinking about and trying to find the best way for an off-chain consensus to be reached. And yeah, so that's about it. We have some links here to our GitHub repos. Cool.